So now in this video, we're going to come back circuit I've been working on, and I kind of shuffled things around and added another 555 timer to it and the circuitry that goes with it. It's kind of circuitry we looked at before, but now we're adding it to other circuitry. Now notice I have, so 5 volts will work with this circuit as long as I have this trim pot to the control pin. I'm actually going to set it to give maximum resistance. Right there from the positive supply. It's 10,000 ohm trim pot. We'll come back to that later. But in case, I gotta adjust the voltage to the control pin. Actually, it's the resistance going to the control pin from the positive supply, but that changes the voltage internally. I talked about that in another video. So it's going to work with 5 volts as long as we use this. It doesn't work as good. Hardly works at 5 volts without this resistor there. So not going to demonstrate that probably, but we need at least 50 milliamps of current right there. Otherwise it starts saying CC, and what that means is that we got, if I do 40 milliamps, we tried to exceed 40 milliamps, but this stopped it, and it does that by lowering the voltage, and I don't want that. So we need at least 50 cc, and here's a 1000 microfarad capacitor. So the long lead of the capacitor there, the positive side is to the positive rail, and then the dash there, shorter lead, is to the negative rail. 1000 microfarad. This buzzer here is sucking a bunch of current right when it switches states, and pulling down the voltage on the board, throwing off the voltage. These components, they look at the supply voltage for their operations, so it's messing things up. This capacitor can provide the current needed for those brief periods of time. This is a 10 microfarad capacitor, so the current going in and out, back and forth I should say, through the buzzer has to be handled by this capacitor, and it will charge and discharge, you know, based on current a lot quicker than this one right there. So this will absorb those voltage changes that this would make otherwise. But in case, yeah, we covered most of this. This one, if I put like a little heat shrink tube or something, I could even probably use this to hold them both in after I remove the alligator clip. I may not need to turn the light off, but as we have it now, I do. So when I say I am adjusting the trim pot to adjust the control pin right there to give it a little less resistance, or a lot less resistance from the positive supply rail, that is what I'm talking about. So turning off the lamp there. I mean, we can leave the lamp on, I'll turn the power on. But there you can hear that steady crackle right there until the light comes on. If I cover it, there you can see crackle goes way down until the light comes on. You know, so if I turn the lamp off, there we go. Now we don't have that problem. I am still covering light coming from the window though. So yeah, there we got kind of a siren. It's a little disappointing. If I wanted a siren, it's actually, I didn't know what sound I would get, to be honest. But we kind of got a siren. I'd want more screech. So now I'm going to turn the trim pot to lower the resistance. I went about halfway there, so I can extend it longer. And okay, that did go down on its own. I thought maybe I'd have to turn it down, but right when I was about to turn it down, it cut down. Now we're going to get that loud crackle again, which is very annoying. So I'm going to turn this off. But in case, my goal was get a circuit that responds to the light. And I made a pretty cool one with the self-flashing light. So they make their own flashing. And I may not have wired this up to get the exact same sound. Probably didn't. And but so far I'm not terribly excited about this. I liked the flashing lights better. You know, I liked half of the time. I didn't like the noise that they made as much during a second half of it. So, you know, I was hoping I could control like LEDs myself and try to get an exact noise I want. And before I move on, I'm going to remove the control pin right there, and we'll see what happens. The jumper that was going between the trim pot and the control pin. And there, you can see it's much more pathetic. That's literally all I did, was remove that jumper. So the capacitor is not charging to as high of a voltage. It's the capacitor voltage that we really need to get this to work right. So now I'm going to try to rush through this. I'm sure people don't find it terribly exciting, but maybe you are interested. So yeah, negative side of that capacitor to the negative rail, positive to the positive rail. Again, it's just when we have current needs, this will briefly provide it so that the power supply doesn't get thrown off. It maintains 5 volts at the supply voltage. So that is a 22,000 ohm resistor, 22,000 ohm resistor to set the timing. And then we have a 100 microfarad capacitor right there. And so I tried 10,000. I didn't like it. I didn't like 33,000. I liked 22,000 for setting the timing. So that sets how long the voltage rises for the most part. And then this one sets how long it discharges. And again, for the most part, because we have the control pin right there. So this raises the voltage that the capacitor needs to charge to, and it raises how low it goes by about 50% right there. So it changes both the rise but more dramatically and the low but less dramatically. Hopefully that makes sense. This diode makes it so we got charge through one resistor and discharge through the other. Otherwise it would charge through 2 resistors and discharge through 1. Discharge is pin 7. That's when it connects to ground, when the output is low. So initially I had LEDs over here. In fact, we don't need this 220 ohm resistor to indicate when the output was high and low, but I'm not going to do that now. I did that in a recent video, and I had planned to do in this one, but oh well. I removed them for something and forgot to put them back. But in any case, we got pin 2 and pin 6 tied together, so they monitor the voltage of the capacitor. Once the voltage gets low enough, pin 2 sets the output high and the capacitor starts charging. Once the voltage gets high enough, because it's not 1/3 and 2/3 anymore, once we attach this, it adjusts. But once pin 6 senses a high enough voltage, then it starts discharging the capacitor, and the output goes low. The output connects to ground. But we're not using the output in this. We're just monitoring the capacitor, charging and discharging. So we have a 100,000 ohm resistor right there. And very important, we have a relatively high value capacitor there. This transistor is a 2N2222 wired as an emitter follower, which is basically a voltage follower, but you lose about 0.6 volts in the process. So if we can get the capacitor voltage up to 4.6 volts, that's what we set it to, whatever, for the high point, then we would have 4.6 volts there, hopefully, unless we got losses, and then we'd lose about 0.6 volts. We could expect about 4 volts coming to the LED. This is a white LED. It needs more than 3 volts. But in any case, that's how this works. I don't know exactly what voltage we got with the capacitor. I did an oscilloscope measurement a couple of videos ago. But yeah, we got 4 volts across the LED and the 100 ohm resistor. So here's that white jumper is the output of the 555 timer right there. That goes to the buzzer, high, low, buzzer only right there. So it's going in between the LED legs right there. And so that's long lead anode, white LED, short lead cathode, resistor in the same row. I don't know how that's going to show up after I process this, but on camera there I can barely see that it is in there. But yeah, same row, 100 ohm resistor right there. So if we did get 4 volts, the white LED is going to drop about 3 volts. That's going to put 1 volt across the 100 ohm resistor. We could get 10 milliamps of current. So that may be best case scenario in this video. That's when the LED gets the brightest. So now, when it comes to the light there, we could wire all of this separately from this right here. They could be completely different circuits. This light dependent resistor, this 555 timer, it's just responding to the light right there. And that's all that's controlling this. We could have completely separate power supplies for both of these halves right there. So it's light dependent resistor. This is, I believe, 0.47 microfarad. I tried, I think that's what that is. No, this is actually a 0.22 microfarad. So it's about a fourth of a microfarad. If I did read that right, I'm pretty sure I did. I was using a 0.474 microfarad capacitor, but I didn't quite like the sound, so I tried to lower them, but I thought I went back. But in any case, that's what we got there. And if it is you know, just crackling, not making a high-pitched noise, you go with the lower value capacitor, and then I should be pointing this, and then it's going to go faster. You know, smaller value capacitor goes faster than a larger value capacitor, all things being equal. And so we got a 1000 ohm resistor there. It does limit the current while it's charging a bit, because we're not getting terribly bright. We could adjust this as well, maybe lower it to get an even higher pitch noise, but we got a pretty high pitch noise. I think I'm happy with what we got. So 1000 for charging, but it doesn't do anything for the discharge. All the discharge just goes through that resistor, so they both add up. But usually this has high enough resistance where it's going to be, you know, quite a bit more than 1000, and it is a lot more than 1000 when it is dark. And so it had so much resistance, the capacitor wasn't even charging and discharging. Otherwise, every time it did, we would have heard the crackle. So this is going to charge to 1/3, or down to 1/3 it's going to discharge, up to 2/3 it's going to charge. It's going to keep bouncing back and forth, regular Astable 555 timer stuff. So now we come to the output, and remember that's pin 3 there. Remember, you got to put pin 4, that's the reset pin up there, pin 4 to the positive supply. If it gets a low signal, you know, close to ground, it resets the 555 timer. It holds the output low no matter what, as long as it has a low input. So we put to the positive supply, it doesn't do anything. So in any case, we're running under the LED there. And as far as this 555 timer is concerned, all we have is circuitry there. That's light. And so we got circuitry coming over there to the long lead of the capacitor, 10 microfarad. And then there's a pin under there. This plus has to go towards the positive side. I don't know what happens if you put it backwards. And then we got on the bottom, you can see plus and minus. There's no epoxy on the bottom of these passive buzzers. So I think, yeah, I reshot a whole scene because I said this was an active buzzer. It's a passive buzzer. And also, there were stuff I didn't like about it, but I would have kept going if I had called it a passive buzzer to begin with. And so yeah, I'll just show you that right now. But yeah, this is going on long enough. But yeah, there's a plus up there, minus. No epoxy. If you see black epoxy filled in, it should be a active buzzer. All the active buzzers I see have epoxy in there, and I'm guessing to protect the circuitry or something. And I don't even know if I'm in the right spot now. There we go. Now I should be in the right spot. Yeah, if there's like epoxy in there filled in, it's probably active, which means you just put like 5 volts across it, and it has an annoying beep, kind of like that screech I got when we had this light the brightest right there. So in any case, yeah, this LED's brightness is following the voltage of this capacitor right here. One reason why I'm using a larger value, so that hopefully it like maintains its voltage better than a smaller one. And because it is going to draw power, but 100,000 ohm resistor right there, probably not much. Maybe even higher value resistor would work even better. I don't know, but we should get the capacitor voltage ultimately to the base there, and then like a little trickle of current goes through, so it may be like slightly lower to the emitter. But what that does is it tells this to start conducting more, and ultimately this basically provides 0.6 volts from the positive supply, less than what you're giving to the base because of that base to emitter drop. Basic voltage follower stuff, emitter follower if you are using an NPN bipolar junction transistor like this. It's also called a common collector, I believe. Again, learn about emitter follower and NPN bipolar junction transistor emitter follower, and you'll know exactly what I mean when I show you this. If this is confusing, you got to learn about that circuit. I can't explain it all from this. But yeah, in any case, this went really long, but I hope you enjoyed. Make sure you check out one of the other videos I posted on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.